This video clip is part of the EPFL introductory course on information computing and communication. It is the third in a set of video clips on information storage and management. It discusses the fundamental issues of naming and addressing stored information. Whether structured or not, an information only makes sense in its own space-time context. For instance, the word Paris does not mean the same thing in Troyes in France in the 21st century as it did in the context of the Trojan War in 1250 BC in what is Turkey today. To be able to identify an information and distinguish it from other information, it needs to have a name or an identifier that tells it apart in the relevant space-time context. Given an unambiguous name or identifier for each piece of information, a directory or catalog is required to locate that given piece of information. That directory or catalog then gives an address at which the piece of information can be found. Given that address, a computer can then issue a request to access the desired piece of information. For the request to reach the address requires that a route or path be defined between the computer and the storage device hosting the information. The present slide aims to underline the difference between these three fundamental information attributes: the way to identify it, i.e. to name or refer to it, the way to locate it, i.e. an address where it is stored, and the way to reach it, i.e. to connect the computer and the storage device hosting the information. This slide gives a set of examples from everyday life to illustrate the notion of information identification by names, localization by addresses, and access over routes. Notice that the same sort of such a reference, for instance an email address in red or the address of a server hosting the corresponding email box in green, may be at the same time a name, an address, or a route, depending on the viewpoint from which one looks at it. An email address may, as the word suggests, be viewed as the address of a named user, and the mail server hosting it as the way to access the mailbox. At the same time, an email address is nothing else but the name on an email box located on some email server that is reachable over some internet route. The last two lines framed on this slide are further examples of digital names, addresses, and routes in the computer context. The first line is about program variables in a computer memory, whereas the second line is about data files in a computer storage system. It is important to observe that all forms of names and addresses, whether physical or digital, have space and time scope attributes. They can exist and be valid for very short or very long periods of time, and they can exist and be meaningful in a strictly local or a global spatial context. This slide gives a few examples of physical names in green, physical addresses in brown, as well as digital names in blue and digital addresses in red, for each combination of these space and time attributes. For instance, talking to you here refers to a person and a place that take different meanings for each person watching this video clip. Similarly, a video clip named Lesson 33 or its address in your computer memory only have a local and temporary meaning because there can be many video clips with the same name in different computers. An ICC section name and room number have temporary meanings because the students and classroom for this course will be different next year. However, they have a broader spatial scope because the course and the room will still exist as such next year. Similarly, the file name given here, or a mobile internet address, are temporary because they may correspond to different objects next year. However, these names and addresses have a broader spatial scope than their local equivalent. Équivalents, or a phone extension number, are perennial because they will always exist. However, they only have local meanings because a phone extension is meaningful only inside its institution, and équivalent has different meanings in different Swiss cantons. Similarly, the video clip named Lesson 33215 and its disk address are perennial because they will retain their meaning next year, yet they have only local meanings because many courses may contain a Lesson 33215 and many computers may know of such a disk address. Finally, the names and addresses now displayed on the top right of this slide have perennial and broad spatial contexts because their meaning stretches across a broad spatial scope and time span. Given the number of ways of referring to information by names and addresses, local or universal, temporary or perennial, there must clearly exist ways that computers can map the ones into the others to go from perennial universal names to temporary local addresses. This is indeed the role of basic computer operating system software. So-called compilers translate programs from programming languages into binary machine language. While doing so, they translate variable names into the addresses that they will occupy when loaded into computer memory. Similarly, file systems and database software manage the movement of data between memory and storage, and while doing so, they translate names of information records into corresponding storage and memory addresses. Consider, for instance, the case of a compiler translating a program designed to extract the roots of a second-degree equation. The program will necessarily contain a section of code to compute a variable called delta equal to the square of b minus 4 times ac, where a, b, and c are the coefficients of the terms of the equation. A, b, and c are symbolic variables that will necessarily need to get addresses when the program is loaded into memory. The program translated in assembler is shown here in the center of the slide. As it generates assembler, the compiler builds a table of all symbolic variables that it encounters and assigns each of them an address that it will occupy in memory. When the binary program is then loaded into memory, the processor executes the instructions and will know where to find the variables that it needs. At execution time, the memory access logic will then route the access requests from the computer to the memory to reach the desired variables in the expected locations.